Hello friends, welcome to EPG Pathshala. Today we shall be learning about global positioning system, that is the second module of our paper, applications of remote sensing and GIS in environmental management. So, in this module you shall be studying about the basic concept of GPS, various segments of GPS, that is space segment, control segment and user segment, the types of lock that exist in GPS. We will also study about assisted GPS technology and the working principle of GPS. After that, we shall be studying about the various navigational satellite systems of other countries besides USA. Towards the end of the module, we shall be studying about the applications of GPS in various domains besides environmental science, such as communication, disaster management, fleet management, vehicle tracking, as well as other applications of farming, communication and so on. Hope you all will learn from this module. So, dear students, after a brief overview of this module, let us start with the introduction of GPS. GPS or Global Positioning System is officially known as Navstar GPS, that is Navigational, Satellite, Timing and Ranging Global Positioning System. The GPS project was first developed in 1973 by the US Department of Defense and was originally run with 24 satellites. This became fully operational in 1994. Roger L. Easton is credited as its inventor generally. These space-bound satellite navigation systems provide location and time information in all the weather conditions. It is maintained by the United States government and is freely accessible to anyone with a GPS receiver. The first GPS satellite PRN-4 was launched on February 22, 1978. Now, coming to the next topic of the module, that is segments of GPS. So, the GPS has three segments: space segment, control segment and user segment. The space segment deals with GPS satellites constellation systems. The control segment describes the ground based time and orbit control prediction. The user segment deals with the various types of existing GPS receivers and its application. So, this figure shows the three segments of GPS. As you can see, the top section of the figure represents the space segment. The bottom portion represents the control segment, that includes various ground bound antennas, while the user segment includes GPS receivers as well as us. So, the first one is space segment, that consists of 21 GPS satellites with an addition of 3 active spares. These satellites are placed in almost 6 circular orbits with an inclination of 55 degree to the equator, and the orbital height of these satellites is about 20,200 kilometers. The orbital period of these satellites is exactly 12 hours of sidereal time, and it provides us repeated satellite configuration, that is every day advanced by 4 minutes with respect to the universal time. Talking about sidereal time, it is the time that is taken by the earth to turn 360 degrees in its rotation. So, there are 6 orbital planes from A to F which are at a separation of 60 degrees at the right ascension which crosses the equator. These orbital planes are centered on the earth. Each plane has about 55 degree tilt relative to earth's equator in order to cover the polar regions. Further, these satellites pass over the same location on earth once each day. The orbits are designed so that at the very least 6 satellites are always within the line of sight from any location on the planet. Powered by solar cells, these satellites continuously orient themselves to point their solar panels towards the sun and their antenna towards the earth. The GPS satellites are broadly divided into 4 blocks. Block 1 that pertains to the development stage, block 2 that represents the production satellites, and block 2 are where replenishment or spare parts of the satellites are dealt with. The 4th block consists of newer satellites and is called block 3, We shall be studying about these blocks in detail in the subsequent slides. So, as I was explaining to you, there are 6 orbital axes, each at an angle of 55 degrees to the equator. The ascension means while moving from pole to pole, when the satellites move from south to north direction, that is ascension node, and descent node is when the satellites move from north to south direction. So, the first block is the navigation development satellite blocks. In this block, 11 satellites were launched between 1978 and 85, weighing about 845 kg in the final orbit. These satellites had a planned average life of 4.5 years, although some of them lasted up to 10 years, thus exceeding their design period. They were capable of giving positioning service for 3 or 4 days without any contact with the control center. The last Block 1 satellite was retired in the late 1995. This test constellation of Block 1 satellites was inclined by 63 degree to the equator instead of the current specification of 55 degree. The second block is Block 2, and together with Block A it constitutes the operational satellites. They consist of 28 satellites in total that were launched from 1989, and many of them are still operating. Block 2 included the launch of 19 satellites between 1989 and 90. None of these satellites are in the constellation today. However, the satellites of Block 2A are in the constellation. They were followed by Block 2R satellites. The first of them was launched in 1989 and the last was decommissioned in 2007. The next one is Block 2R, that is the replacement operational satellites. The first launch of the next block, Block 2R, was in January of 1997 and it was an unsuccessful attempt. The following launch in July of 1997 succeeded, and these satellites have a planned average lifespan of about 10 years. They have the capability to measure distances between themselves and transmit data to other satellites or the control segment. Again, the Block 2RM includes the modernized satellites, and of this block, the first satellite was launched in September of 2005. There are about 8 satellites in this series, and these satellites were modified and upgraded so that they radiate 2 new codes, that is a military code called as M code and civilian code called as L2C code, and it also demonstrates a new carrier, that is L5. The Block 2F includes the follow-on operational satellites. Block 2F is the most recent group of GPS satellites, and among them the first satellite reached the orbit in May of 2010. The design life is about 12 to 15 years. Block 2F satellites have faster processors and more memory on board. They broadcast all of the previously mentioned signals and one more, a new carrier, that is known as L5. The Block 2F satellites will replace the Block 2A satellites as they age. The next in the series is Block 3 satellites, which are the new generation of GPS satellites, and they have introduced significant enhancements in the navigational capabilities by improving the interoperability and signal jam resistance. They provide the fourth civil signal on L1 band, and the first launch is expected in about 2017. The second segment is the control segment, which monitors and controls the satellite system continuously. It also determines the GPS system time. It predicts the satellite ephemeris and the behavior of each satellite clock. It is updated periodically, and the navigation message for each particular satellite is controlled. The control station consists of 3 entities: master control system, monitor stations and ground antennas. This figure shows the master control station, alternate master control stations, ground antennas, remote tracking stations, as well as the Air Force and NGA monitor stations. The master control station is located at Falcon Air Base in Colorado Springs, that is in Colorado, and is responsible for the overall management of remote monitoring and transmission sites. GPS ephemeris is the tabulation of computed positions, velocities and derived right ascension and declination of GPS satellites at specific times for eventual upload to GPS satellites. Coming to the monitor stations, 6 monitor stations are located at Falcon Air Force Base in Colorado, Cape Canaveral, Florida, Hawaii, Ascension Island in the Atlantic Ocean, Diego Garcia Atoll in the Indian Ocean and Kwajalein Island in the South Pacific Ocean. Each of the monitor stations check the exact altitude, position, speed and overall health of the orbiting satellites. The control segment uses measurements collected by the monitor stations to predict the behavior of each satellite's orbit and clock. The prediction data is then uplinked or transmitted to the satellites or transmission back to the users. The control segment also ensures that the GPS satellite orbits and clocks remain within acceptable limits. A station can track up to 11 satellites at a time. This checkup is performed twice a day by each station as the satellites complete their journeys around the earth. Variations caused during such periods, such as by the gravity of moon, sun and the pressure of solar radiations, are passed along to the master control station. So, the main tasks that are performed by the control segment are the following. First is the monitoring and control of satellite orbital parameters, monitoring the health and status of the satellite subsystems, activation of spare satellites if required, update of parameters in the navigation message that includes ephemeris, almanac and clock corrections, resolving the satellite anomalies, controlling selective availability and anti-spoofing as well as the passive tracking of the satellites. The ground antennas, they monitor and track the satellites from horizon to horizon. They also transmit correction information to the individual satellites. These antennas are used to communicate with the GPS satellites for command and control purposes via S-band radio signals. The data includes ephemeris and clock correction information that is transmitted within the navigation message as well as command telemetry from the master control station. The third and the last segment is the user segment, which is generally a GPS receiver. These GPS receivers are generally composed of an antenna tuned to the frequencies transmitted by the satellites, receiver processors and a highly stable clock, which is commonly a crystal oscillator. It is capable of determining the user position, velocity and precise time by processing the signal broadcasted by satellites. They can also include a display for showing location and speed information to the user. A receiver is often described by its number of channels, and this signifies how many satellites it can monitor simultaneously. So, as I discussed earlier also the types of GPS data, the GPS satellites can broadcast two different types of data. The first is almanac and the second is ephemeris. The almanac sends the time and status information about the satellites, while the ephemeris has orbital information that allows the receiver to calculate the position of the satellite. This data is included in the 37,500 bit navigation message, which takes about 12.5 minutes to be sent at 50 bits per second. After studying about the segments of GPS, let us come to the working principle of GPS, that is how the GPS works. So, GPS is actually a constellation of 27 Earth orbiting satellites, out of which currently 24 are in operation and 3 are kept in reserve. Each of these 3,000 to 4,000 pound solar powered satellites circle the globe at about 19,000 to 20,000 kilometers altitude, making 2 complete rotations every day. These orbits are arranged so that at any time anywhere on the earth there are at least 4 satellites visible in the sky. So, what a GPS receiver does is it locates 4 or more of these satellites, figures out the distance to each and uses this information to deduce its own location. This operation is based on a simple mathematical principle called as trilateration. So, in this figure you can see the satellites that are orbiting in the sky. In this figure there are 4 satellites that are visible and the GPS receiver is the green tractor shown in the middle of the figure. The control station and the antenna are also visible towards the left hand side of the figure. This is the principle of trilateration that I was discussing. For example, if we have to find out location at the green dot, we have to visualize minimum 3 satellites that are visible in the sky. For each satellite, let us say the first one as the A satellite. For each satellite, its position can be determined by the red circle that is shown around a single satellite. So, when we have the red circles for all these satellites, the common areas of intersection between 2 satellites will reduce the error. Accordingly, when we include the third satellite also, the intersection point of all these 3 satellites will give you the absolute location of a place. This figure shows the visible satellites at a given blue dot, that is a receiver, at any point of time which keeps on changing. After this, let us come to the types of locks that are present in GPS. So, getting a lock on by the GPS receivers on the ground, it usually takes some time if the receiver is in a moving vehicle or in dense urban areas. So, the initial time that is needed for a GPS lock is usually dependent on how the GPS receiver starts. Accordingly, we have 3 types of start: hot start, warm start and cold start. The hot start is when the GPS device remembers its last calculated positions and the satellites in view, the almanac used, that is the information about the satellites in constellation, the universal coordinated time, and then it makes an attempt to lock onto the same satellites and calculate a new position based upon the previous information. This is the quickest type of GPS locks, but it works only in the conditions when we are at the same location as you were last when the GPS was turned off. The second one is the warm start, where the GPS device remembers its last calculated position, almanac used, and the universal coordinated time, but not which of the satellites were in view. So, accordingly, then the GPS performs a reset and attempts to obtain the satellite signals and calculates a new position. So, the receiver has a general idea of which satellites to look for because it knows its last position, and the almanac data helps identify which satellites were visible in the sky. This takes usually a longer time than the hot start, but not as long as the cold start. So, finally, the cold start is when the GPS device dumps all its information and it attempts to locate the satellites and then calculates a GPS lock. This takes the longest because there is no known prior information. So, the GPS receiver, it has to attempt to lock onto a satellite signal from any available satellites, basically like polling, which takes a lot longer than knowing which satellites to look for. This GPS takes the longest time among all the locks. There is also an example of assisted GPS technology, where the GPS downloads the current ephemeris for a few days ahead via the wireless networks and helps to triangulate the general user's position with the cell towers, thus allowing the GPS receiver to get a faster lock at the expense of several kilobytes. After studying the working principle and the locks in GPS, let us study the other types of navigational satellite systems or GPS systems. So, Besides the US based GPS system, we have Russian GLONASS, that is Global Navigational Satellite System, European Union's Galileo, Chinese BeiDou Navigational System, and India's Indian Regional Navigational Satellite System. GLONASS navigational satellite system has been developed by Russia, that was originally Soviet Union in 1976. It has a network of 24 satellites that cover the earth. Currently, the US based GPS satellite has a network of 31 satellites which cover the planet and have been used in commercial devices as well, besides its military applications. So, this image, it shows the orbit and constellation of GLONASS on the left side and GPS system on the right side. Let us look at the differences between these two constellation systems. So, dear students, looking at their comparative table, as we already discussed, GLONASS is Russian based navigational satellite system, while GPS is of United States of America. The coding in both differs, as GLONASS is FGMA based while GPS is CDMA based. We also discussed that GLONASS is a constellation of 24 satellites while GPS is of 31 satellites. The orbital height of these two systems is more or less comparable, with GLONASS being at 21,000 kilometers altitude and GPS at 19,000. The accuracy is also comparable, with GLONASS between 5 to 10 meters and GPS between 3.5 to 7.8 meters. The orbital plane inclination of GLONASS is 64.8, while the next is 55 degree. The orbital period of Russian based GLONASS is about 11 hours and 16 minutes, while that of GPS is 11 hours and 58 minutes. Currently, both of these are operational. So, coming to the advantages of GLONASS over GS, as such, there is no clear advantage of GLONASS over GPS other than accuracy. When used alone, it does not have that strong coverage as GPS has, but when both these systems are used together, they increase the accuracy along with the coverage. Also, it is very useful in northern latitudes, as Russia started GLONASS specifically for Russian region. The accuracy of GLONASS can be achieved up to 2 meters as well. So, if we are stuck in a place where GPS signals cannot be received, such as between huge buildings or subways, we can be tracked by GLONASS satellites accurately. The commercial use of GLONASS was in car navigator in the form of GLOSpace SGK-70, but it was very bulky and quite expensive. The next one is European Union's Galileo positioning system. Unlike GPS and GLONASS, Galileo system was conceived and developed to be under civilian control only, but it is also 100% interoperable with GPS and GLONASS. So, it makes it a fully integrated new element in the worldwide global navigational system. It is also a powerful cornerstone that will allow more accurate and more reliable positioning even in high-rise cities where buildings can obscure the signals. It is creating a new range of business opportunities for equipment manufacturers, application developers and providers of reliability critical services, and all these applications are related to peaceful uses of positioning system. One of the aims of this Galileo is to provide an indigenous alternative high precision positioning system on which these European nations can rely independently from Russian GLONASS and US GPS systems. This high precision capabilities will be available for paying commercial users, and it is also intended to provide horizontal and vertical positioning measurements within 1 meter precision and better positioning at higher latitudes. In December 2010, the European Union ministers in Brussels voted Prague in Czech Republic as the headquarters of Galileo project. In this operation, Galileo will use 2 ground operation centers near Munich in Germany and Fucino in Italy. out of these satellite systems in Galileo, in October 21st, 2011, the first two of the four operational satellites were launched, while the next two satellites of Galileo system were launched on 12th October 2012. On 22nd August 2014, the fifth and the sixth satellites were launched, but were injected into an incorrect orbit. However, these orbits have now been corrected and at the cost of reduced propellant, but thus shortening the lifespan of these satellites to 12 years. On 27th March 2015, the 7th and 8th satellites were launched successfully using a Soyuz 4 space launcher. The next in the series is Chinese Navigational Satellite System, which is called as Beidou Navigational Satellite System, and it consists of two separate constellations and has been operating since 2010, but will be fully functional and will start serving the global customers by 2020. Now, coming to the Indian Regional Navigational Satellite System, it is an independent satellite system being developed by India. It is designed to provide accurate position information service to users in India as well as the region extending up to 1500 kilometers from its boundary, which is its primary service area. Also, an extended service area lies between primary service area and the area that is enclosed if we consider a rectangle from 30° south latitude to 50° north latitude and 30° east longitude to 130° east longitude. This Indian Regional Navigational Satellite System will provide two types of services. The first one is standard positioning service, which is provided to all the users, and restricted service, which is an encrypted service provided only to the authorized users. It is expected to provide a position accuracy of better than 20 meters in the primary service area. The space segment of IRNSS consists of 3 satellites in geostationary orbit and 4 satellites in geosynchronous orbit with an inclination of 29° to the equator plane. The constellation of these 7 satellites was named as NAVIC, that stands for Navigation with Indian Constellation, by the Honorable Prime Minister of India, Mr. Narendra Modi, during the launch of 7th satellite. All the satellites will be visible at all times in the Indian region. The ground segment is responsible for the maintenance and operation of the IRNSS constellation, and it provides the monitoring of the status, computation of the orbital and clock parameters, as well as navigation data uploading. This data from the IRNSS satellites would be helpful in the following fields, such as missile targeting, which is one of the military applications. Besides, it will also be helpful for disaster management, vehicle tracking, fleet management, marine navigation, mapping and geodetic data capture, precise timing, visual and voice navigation for drivers, as well as integration with mobile phones along with terrestrial, aerial and marine navigation. It will also help in terrestrial navigation aid for hikers and travelers. So, the first satellite of this series was launched on 1st July 2013 from Satish Dhawan Space Center, Sriharikota, by the vehicle PSLV C-22, and it was put into a geostationary orbit carrying two types of payloads, navigation payload and ranging payload. Its liftoff mass was 1425 kg. IRNSS-1B is the second navigational satellite of the series that was successfully launched on April 4th, 2014, and is placed at 55° east longitude. All its configuration is similar to the first one and has been released in less than 7 months after the launch of 1A. It also carries two types of payloads similar to IRNSS-1A, and the launch vehicle was PSLV C-24. The third satellite in the series is IRNSS-1C, and it was launched successfully on 16th October 2014 from Satish Dhawan Space Center and placed in geostationary orbit. with a lift off mass of 1425.4 kg. This satellite is powered by two solar arrays which generate power up to 1660 watts and has a lifetime of 10 years. It also carries two types of loads similar to its predecessors, navigation payload and ranging payload. The fourth satellite is 1D, which was launched on March 28, 2015 by PSLV C-27 and also has a lift off mass of 1425 kg. It also has the same configuration as its predecessors and was launched into a sub-geosynchronous transfer orbit with a 284 km perigee and 20,650 kilometers apogee with an inclination of 19.2 degree with respect to equatorial plane. The fifth one is IRNSS-1E that was launched on January 20, 2016 from same Satish Dhawan Space Center. It also has similar configuration and lift off mass like its predecessors and carries two types of payloads. The navigation payload, which transmits the navigation service signals to the users, and the ranging payload, which facilitates accurate determination of the range of satellites. The sixth one is the IRNSS-1F, which was launched on March 10, 2016 and was launched by PSLV C-32 into sub-geosynchronous transfer orbit from Satish Dhawan Space Center. The seventh and the last in the series is IRNSS-1G that was launched by PSLV C-33 into sub-geosynchronous transfer orbit on April 28, 2016 from Satish Dhawan Space Center, Sriharikota. IRNSS-1H is the 8th satellite that was planned to be launched by PSLV C-39 into sub-geosynchronous transfer orbit with a 284 km perigee and 20,650 km apogee. However, it could not be placed into the orbit as the mission was unsuccessful. Let us also talk about Gagan, which is GPS aided geo augmented navigation when we are talking about the navigational satellite systems. It is a satellite based augmentation system implemented jointly with Airport Authority of India. Its main objective is to provide satellite based navigation services with accuracy and integrity that is required for civil aviation applications. It also has to provide better air traffic management over Indian airspace. So, this system is interoperable with other international SPS systems and provides seamless navigation across regional boundaries. The first Gagan navigation payload was flown on GSAT-8 and it was launched on May 21, 2011, while the second on September 29, 2012. So, after this, let us talk briefly about some of the applications of GPS, as the applications are very varied. So, the first of this is the road transport, which includes commercial fleet management and freight tracking, taxi services, monitoring of public transport, emergency vehicle location, dispatch as well as navigation. This has also been adopted widely by the private car owners, and most automobile manufacturers now release new vehicles with optional factory fitted GPS. The second is aviation, and we know almost all modern aircraft are fitted with multiple GPS receivers. This provides pilots as well as passengers with a real time aircraft position and map of each flight's progress. It also allows the airline operators to pre-select the safest, fastest and most fuel efficient routes to each destination. Besides, it is also used for resource mapping and aerial surveying by the unmanned aerial vehicles. The third one is marine application, which includes ocean as well as inshore navigation, dredging, port approaches, harbor entrance and docking, vessel traffic services, automatic identification systems, hydrography and cargo handling. It is also used to position and map dredging operations in rivers, wharves as well as sandbars. The next in this category is rail transport, and these systems throughout the world use GPS to track the movement of locomotives, rail cars, maintenance vehicles, as well as the wayside equipment in real time. When combined with other sensors, computers and communication systems, these improve the rail safety, security and operational effectiveness. Modern railways also are fielding positive train control systems in various countries to prevent the collision, derailment, work zone incursions as well as passage through switches in the wrong position. Besides rail transport, GPS is increasingly used in heavy vehicle guidance to guide and track heavy vehicles in engineering applications such as mining and construction. In open cut mines, GPS is integrated into application developed by companies such as Leica Geosystem, Topcon Positioning System and Trimble or Caterpillar. In other professional applications, GPS information is captured by sophisticated IT systems and meshed with other engineering applications. Besides, GPS also has applications in farming, such as for mapping the plantations and ensuring that the farmers can return exactly to the same areas when sowing their seeds for plantations. It also allows farmers to continue working in low visibility conditions such as fog and darkness, as each piece of machinery is guided by its GPS position. High accuracy GPS is also used to map soil sample location, allowing farmers to see where the soil is most fertile across individual field or even entire farms. The scientists also use GPS for wildlife monitoring or tracking by using GPS collars or tags that automatically log the animal's movement and transmit the information via satellite back to the researchers. It is also used by earth scientists for research work, such as by installing the receivers on glaciers or landslides. The scientists can observe and study both the speed and direction of movement, helping them to understand how the changes are occurring in the landscape over time. Similarly, GPS receivers can also be installed on solid bedrock to help understand the changes that are occurring in tectonic plate motions across the world. Further, GPS is also used for surveying and mapping applications, such as mapping and measuring the features on the earth's surface and underwater with very high accuracy, and determining the land boundaries, monitoring changes in the shape or structure of sea floor, and for positioning the survey marks, buildings, bridges and other large infrastructure. It is also widely used in mapping, including aerial mapping and GIS applications. In geophysics, GPS is used to timestamp seismic activity and to monitor position changes in sensitive physical formations such as volcanoes and earthquake fault lines. Besides this, GPS is also used in security applications for tracking of vehicles, containers, other valuable cargoes and covert tracking of suspects. GPS is also important for telecommunication applications, particularly for mobile telephone networks. Global financial systems increasingly need precise timing systems to schedule and prioritize local and international money transfer, settlements and trades, and to provide an audit trail for financial transactions, for which GPS is increasingly being employed. Besides, GPS is also used in a variety of social activities, and we have GPS based social networking, geotagging photographs, cross country cycling, hiking, skiing, paragliding, skydiving, geocaching and other gaming activities. So, dear students, to summarize, I hope by the end of this module you shall have understood the basic segments of GPS, what are the types of lock systems in GPS as well as the working principle of GPS. I hope you would also be able to appreciate the various types of space agencies around the world that have their own navigational satellite systems. Also, you would appreciate the various applications of GPS in other domains also besides environmental sciences, such as communication, such as transport system as well as disaster management, vehicle tracking and fleet management. I hope you all have benefited from this module. Thank you.